Hi kids, here is the second content video for this day, and this time I'm not embedding my webcam, so maybe we'll take a poll at some point as to do you like it with the webcam or do you like it with no webcam? We'll see. All right, so 12 basic functions. So there are tons and tons of functions, right? But there are certain ones that are so common that you want to get to know them really well. And, along with their characteristics, domain and range, and, right, are there any breaks, continuity, right? All those things that we talked about yesterday, and behavior, or not yesterday, but the last content video. These ones should, a picture of these should be able to pop into your head. And you should be able to come up with those characteristics relatively quickly. So here is the first one, the identity function. We call this the identity function because it looks like y is the same as x. So in other words, when the domain is 1, the range is 1. When the domain is 2, the range is 2, and so on and so forth, right? So the domain is the range, y equals x, right? Which is a linear function, passes through the origin, cuts quadrant 1 and 3 at a 45-degree angle, right? So that's your basic linear function. Now I can manipulate that function, right? I can move it up, down, right, left, flip it, make the dilation factor negative, all that kind of stuff. Stretch it, flat, make it more less steep and more steep, all that kind of stuff. But this is the basic identity function. And it is a polynomial, right? X to the first. And then, of course, we have the squaring function, y equals x squared, with a domain that is not, which is infinite, but a range that is not, right? The squaring function has an absolute min or an absolute max, and the end behavior, right, is infinite, but is the same. Both ends either go up or both ends go down, as opposed to a line where the ends do the opposite thing. So now the next function I'm going to leave, the next basic function, I'm going to leave polynomials, but you should be aware from Algebra 2 that y equals x cubed, the end behavior is like y equals x. So is x to the 5th, so is x to the 7th. In other words, any odd, not unfunction, odd degreed function has the end behavior like x to the 1st. Similarly, any even degreed, not even function, even degreed polynomial has the end behavior like a quadratic. Both ends go up or both ends go down. You might have different stuff happening in the middle when it's x to the 4th, but the ends behave like a quadratic. All odd degree polynomials behave at the ends like a linear polynomial. All even degreed polynomials behave like a quadratic does at the ends. That's why Algebra 1 is lines and quadratics, and Algebra 2 starts with lines and quadratics again before, right? They are the building blocks of all polynomial functions. Oh, I did have the cubic function, I'm sorry. So the cube function, and so here you can see again what I'm talking about. Cube function is like a snake, right? But notice that the end behavior, because the leading coefficient is positive, is the same end behavior as x to the 1st. Notice, though, that the identity function is a straight diagonal line. The squaring function is always concave up. The cube function, remember, has a point of inflection. We did this in AF, where the cube function changes from concave down to concave up at the point of inflection. Not a turning point, but a point of inflection. The reciprocal function, right? F of x is 1 over x, right? So the range is 1 over the domain, all the domain values. And since x is in the denominator, x cannot be 0. So there is a vertical asymptote and infinite discontinuity at x is always 0, right? Notice that, so there is a continuity break, whereas the identity, squaring, and cubic function are all continuous because they're polynomials. A rational function has a break in it. Not all rational functions have breaks because it just depends upon what makes the denominator equal to 0. This rational function also has a horizontal asymptote, right? There's two branches in quadrant 1 and 2. It's also it's a hyperbola, right? That's shifted off of like a diagonal hyperbola. No turning points. The reciprocal function only decreases. No turning points. The greatest integer function, remember, is not that, right? It's not that important. I mean, I shouldn't say it's not that important. It's not that common, but it is really, the greatest integer function does have a lot of applications in computer science, and a little bit in calculus as we investigate something called right and left hand limits. But notice the greatest integer function, right, has closed dots and then open dots. The greatest integer function means that you can input any x, but your output is only integers. Remember, double bar z means integers. So when you input 0, you get 0 out. When you input a half, you get 0. When you input 3/4, you get 0. But when you input 1, you get 1 back out. 1.1 defaults back to 1. 1.5 defaults back to 1. 1.9 defaults back to 1. But when you input 2, you get 2 out, right? We also call this the step function because it looks like a bunch of steps. The square root function, notice the square root function is half of a parabola, sideways parabola, right? It's the top half because it is a function. A sideways parabola, a full sideways parabola is not a function, right? This is y is equal to the square root of x. That's why when you input, for instance, 4 into the square root function, the square root of x is 2, not plus and minus 2, 2. Because when you put in 4, you can only get out one number, right? But when I put 2 into this function, when I put 4 into the red function, the square root of 4 is 2, negate it, that's when I get this point. Whoops, sorry. But you cannot have, right, this entire sideways parabola has an equation x is equal to y squared, and that is not a function because when you input 4, the domain value of 4 has 2 different ranges. That breaks the function rules, right? Can't have it. Can't have it. The absolute value function is really a very fancy piecewise function where it is 2 linear functions. Y is equal to negative x on the left side and y is equal to positive x on the right side. Right? Notice it is a very harsh turning point. Unlike x squared that has a smooth turning point at 0, absolute value has a very harsh turning point. The exponential function, right? Your basic exponential function, whether it's e to the x, 2 to the x, as long as that base is greater than 1, your exponential function looks like this, has a y-intercept of 0, 1, and a horizontal asymptote at y equals 0, because there is no x, no matter what your domain that you put on this number, and remember, e is just 2.7, right? It's 2.7-ish. Right? It's a number a little bit smaller than 3. Pi is a number a little bit bigger than 3. E is a number a little bit smaller than 3. But they're non-terminating, non-repeating decimals that are not as a result of any radical. They're called transcendental numbers. There's tons of transcendental numbers. Go ahead and ask me another one. Go ahead. Besides e and pi. Go ahead, ask me another one. Okay, you asked me. I don't know. You know why I don't know what the other ones are? Because they ain't famous. Pi and e are famous. That's why they were named pi and e instead of 3.14159, blah, 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 and 2.7, 1828, 1828, 4590, 45, dot, 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 dot. Okay? So e is a number slightly smaller than 3. Pi is a number slightly bigger than 3. End. But no matter what your base is, you can't raise a base to any domain value that will yield 0, which is why you have a horizontal asymptote at 0. The natural log function, right, is just the inverse to e to the x, right? So instead of a horizontal asymptote at y equals 0, there is a vertical asymptote at x equals 0. Instead of sliding slowly around the horizontal asymptote to the y-intercept of 0, 1, you slide along the vertical asymptote quickly to an x-intercept of 1, 0. Instead of swooshing quickly like the exponential function does after the y-intercept, the log function does the inverse. It swooshes slowly after the x-intercept. Sine function, right? We studied these in AF and we will study them again. Sine function, you need to know, is bounded above at 1 and below by -1, right? These are the absolute maxes, the absolute mins, and the zeros, the x-intercepts, are at 0, pi, and 2 pi, right? And then the sine function is also not an odd degree function, it's just an odd function because you should be able to see the point symmetry around the origin, as opposed to cosine. Cosine is just a shift of the sine function, but it's such a special shift that it has its own name called cosine, right? Cosine is also bounded above and below by 1 and -1. All the range values bounce back in between those two values. Absolute maxes at +1, absolute minimums at -1. But the x-intercepts on cosine are at pi/2 and 3 pi/2. Cosine is not an even degreed function, it's an even function. You should be able to see the symmetry across the y-axis. Now this last one, the logistic function, is not really one that you should know, right? So don't worry about this one. It is a function that we will start to deal with very, very briefly in our class, and then we will deal with it again in calculus. But notice what it is a merge of exponential and logs, right? So do you see the exponential piece here? Slide along the horizontal asymptote, right, up to an intercept. And then you have the log function after that, where you swoosh, but swoosh slowly. Now the log function does grow without bound, right? It grows just very, very slowly. The logistic function does have a maximum. It is bounded above and below. But again, do not worry so much about the logistic function. I just didn't want to have 11 basic functions, right? I needed to have 12. Piecewise functions. Piecewise functions are important, but they are not as important as the functions we just did. Piecewise functions are just combos, right? It's like, right? It's like when you go to the cafeteria and you pick for your salad some, I'm going to put garbanzo beans on and I'm going to put some sunflower seeds on. Oh, but and I'm putting them together when normally I wouldn't have garbanzo beans and sunflower seeds together. So here, piecewise functions are just a way to graph the same function, multiple functions, on the same grid. So this is a piecewise function where you're going to graph function 1 on this domain and function 2 on this domain. So this is the break between the two different domains. So I'm going to erase this eventually, but I'm going to tell myself that I have two different graphs to draw where x is equal to 0. So then I am going to go and I am going to draw when x is greater than or equal to 0, that is to the right, and the rule I'm supposed to use is x. So when put 0 into x and I get 0 with a closed circle. Put 1 in and I get 1. Put 2 in and I get 2, blah, 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 blah. There's part of my identity function. Then I'm going to draw to the left of my break, right? My domain break. And what am I going to draw? The opposite of x. So I can't put in 0 because I don't have an equal sign here, but I can put in -1. If I put in -1, negate -1, and I get 1. Negate -2, and I get 2. Oh, hey. Hey. Hello, what is that graph? Do you recognize it? This is such a famous piecewise function, it got its own name. And you know what its name is? Yep, you got it. You need to understand that absolute value isn't real, right? It's not it's real. It's not an operator. You can't distribute into absolute value. There's no inverse operation to absolute value because this is actually the definition of absolute value. This is the real function's name. This is just mathematicians' shorthand notation for a very famous piecewise function. Crazy. All right, let's graph the next one, the next piecewise function. So this time I have 3 functions. 1, 2, and 3. This is the domain 1, which is to the left. This is domain 2, which is only at a point. This is domain 3, which is to the right. And it's to the right of what number? Where's my break? That's it, 1. So I'm going to draw this break at 1. And I should erase it. I should have erased this one, right? This is a fake break. This is just me reminding myself that at 1, I have 3 different things to do. So x squared. What does x squared look like when I start at 1? When x is 1, x squared is also 1, right? But I have to put an open circle there. Do you see why? Check. When x is exactly equal to 1, I'm supposed to graph level 1. Oh, hey, that open circle just got filled in. Whoop, whoop. Ooh, it's raining. Oh, whoops, silly. I didn't finish this, did I? I had an open circle, and then I'm supposed to draw in when x is 0, right? Give me numbers less than 1. So for instance, 0. 0 squared is 0. -1 squared is 1. -2 squared is 4. So that was an open circle, and then the squaring function. Oh, I'm so terrible. Oh, that's so heinously ugly. No judging. Then I filled in the circle because I did that value. It seemed kind of silly. Why didn't they just put an equal sign there if they wanted that? Now to the right of 1, I have to use this rule. So I'm not allowed to put in 1, but if I was, I would be starting here at 1. So I have another open circle. So right here, there's 2 open circles and a full one and a closed one. Now the closed one rules, right? You can't see the open circles because it was filled. But now I have to draw when I have to, what number is bigger than 1? So like 2. When x is equal to 2, the range is a half. When x is equal to 3, the range is a third. When x is equal to 4, the range is a fourth. There's a horizontal asymptote on the right. Now, remember, you should erase this, right? That was just while I was drawing. So that graph is not attractive. It is continuous, though, but it's not an attractive graph, and it's not one that I come across very often because it's piecewise. Now, imagine that I had left this as an open circle and, right, 2 open circles, because let's pretend that this, when x was 1, I was supposed to graph a dot at 2. That's what that graph would look like, right? So let me draw that a little bit better. Let me draw that over here. It would be quadratic to 1, open circle. At 1 would be at a level 2. After one would be another open circle, and then the reciprocal function. Right? Kind of ugly, really. All right, so that's it for the content videos. So what we will do in class, in live class, is do some more examples of these and practice and be able to start your homework with this and work together and ask me questions. Right? Have a good one.